As my computer broke over winter break for some reason. It was unplugged on a desk by itself and it broke. No one ever came in here. All my stuff was undisturbed and it just broke. I'm at complete loss. But I'm having to make do with this. There we go. Can you see paper? Alright, hopefully this all works. So today we're going to be looking at momentum. This is the one subject that I really should teach earlier. But at the same time, energy is very important, and I should teach that first. I should totally teach this before rotational. I need to reorganize this next year. Because I taught rotational momentum before I taught momentum. But momentum is a very important concept. So momentum is equal to mass times velocity. Now, it's also one of the, and when I say momentum by itself, I mean linear momentum. We represent this with a lowercase p equal to mass times velocity. It is one of the fundamentally conserved things in the universe. What this means is, given an isolated system where no external forces are applied to it, it stays constant. Whenever you drop a ball, so let's say that we have the Earth and we have a ball above it. If you're holding it still, it's not moving, so its momentum is 0. And when you release it, it starts moving. It gains momentum. How is that possible? When momentum is constant and doesn't change, it can neither increase or decrease. So when I let go of the ball, how does it gain momentum? When I just said that it's conserved and cannot increase or decrease or be destroyed or created. I'll give you a hint. So remember that velocity is a vector. And this is a scalar, it's just a number. That means a scalar times a vector has to equal another vector. A vector has a direction. So what also happens when you drop a ball? Gravity pulls it down, but what else? So let me think about this. So an object not accelerating has no external forces on it. And if I push on this, and another force pushes back on it, and if these two forces are equal, it's the same thing as a box with no forces on it, right? Because they both cancel each other out. So what happens when you drop a ball? Earth moves upward. Now, of course, it has to cancel it out. Now, of course, this has a very small mass compared to Earth, and so we can get high velocities. But this has such a big mass that the velocity is so negligible that you can't even see it. That's the reason why there's an apparent creation of momentum whenever you release a ball. It's actually because Earth is moving up with such a speed, it cancels out that momentum. Another thing, when you're dropping a ball onto the ground and it just sticks there. What's happening is you're causing atoms, molecules, to be moving with whatever direction, momentum. They'll be oscillating more downward. Of course, they'll hit other atoms, will continue the momentum throughout it, and it'll continue in that direction. Another thing that could happen is Earth could be slightly moved downward. You can gain some, again, it's so small of a velocity on Earth that it's almost negligible. We're talking about it moving at a fraction of a fraction of a fraction of the width of a proton per second. Something that's immeasurable, but that's the reason why it appears as if momentum is destroyed whenever you drop something that stops on the ground. What you're doing is you're giving a velocity to the entire Earth, but because Earth's mass is so much larger, it almost absorbs it and makes it seem like it gets rid of it. So let's look at so again, it's important to know that momentum is always conserved. This is actually stronger than energy is always. I can't really say that. I told you that energy is always conserved, too, and it is, unless you get into very super high advanced physics. But energy can transform forms. It can go from kinetic energy into potential energy or into thermal energy. And we usually say that thermal energy is lost because it's not useful. We can't really use thermal energy, at least whenever it's high entropy. But we have something known as elastic collisions and elastic collisions. This is where momentum is useful. So let's look at elastic collisions versus inelastic collisions. What do you think elastic and inelastic means? What is elastic? You hear the word elastic. What do you? So like a rubber band. So in both of these, momentum is conserved. There is only one truly elastic collision, and that is between atoms. But we can in this world, again, we assume no friction, we assume no air, we assume we're in a perfect vacuum. Um, we'll assume that we can have elastic collisions, but it's an elastic collision is the objects colliding aren't deformed, are smashed, meaning they perfectly bounce. Don't think of rubber. I mean, rubber is kind of good, but think billiard balls. colliding. So if you have a billiard ball, pool ball, and they hit, what happens is they can't deform too well, and so all the momentum is transferred from one object to another, or whatever. Another thing, the key principle. I should start this. The key principle is no kinetic energy is lost. Meaning kinetic energy is conserved. Kinetic energy is the energy of motion. Now, even though energy is conserved, kinetic energy can be turned into potential energy or into thermal energy. And usually when kinetic energy is lost, it's due to thermal energy being created. Thermal energy is actually kinetic energy in itself. Thermal energy is so temperature is how fast the atoms are moving. Temperature is actually the average kinetic energy of all the molecules. And so what happens is when we say no kinetic energy is lost, we're saying that all the kinetic energy stays in the billiard balls, whatever. Inelastic collision is a collision in which kinetic energy is lost. So I just said that one example of kinetic energy being lost is heat generated. Do you know? Can you think of another example of some energy whenever two things are whenever two things hit? Where do you think some of the energy goes to? So some of it's transferred as thermal or heat energy. What's another thing you can think of? Mm-mm. We're talking about converting kinetic energy into another form of energy. Do you hear it? Do you hear whenever two things match? Sound. So the energy may be transformed into sound, deformation of materials, flying debris. So if you drop it in sand and the sand goes up, the sand gains still some of the kinetic energy, etc. Thermal energy should be included. Here's one. Often objects stick together. Or interlock. And often objects are also deformed or crushed. But momentum is always conserved. So even though the kinetic energy is being lost, the momentum in the equations will be conserved. So this will be this is a situation in which if you only apply conservation of energy, if you don't keep track of where all the energy is going to, you can end up getting wrong results. But momentum can be more powerful because momentum is always going to be conserved. As long as you don't have any other objects, like for example, the Earth, as long as we don't include gravity in it, Because if something's falling due to gravity, that means Earth is moving up. So you would have to account for the fact that you're adding momentum to, opposite in direction to the Earth, which cancels out the momentum you're gaining there. As long as your system is completely isolated, and your momentum is conserved, you can do some powerful things with it. If you can keep track of all the energy, then you can also use conservation of energy to do it. For example, we know the potential energy due to gravity. So that means we can do the roller coaster examples using conservation of energy. So let's do an example. And I'm going to do an inelastic collision. So kinetic energy is not going to be conserved. Let's suppose we have a box that has 5 kilograms of mass and it's moving at 10 meters per second, and it hits another box that is 10 kilograms. So this would be the before the collision. And after the collision, they stick together and move at some velocity. My question is, what is this final speed or velocity? So we know that momentum is always conserved. So we can do it before and after, and we know that the total momentum is going to stay the same. So we add up all the momentum on the left side. Recall that momentum is mass times velocity. So we have 5 kilograms times 10 meters per second plus 10 kilograms times 0 meters per second. 0 times 10 cancels out. 5 times 10 is 50 kilogram meters per second. And this is also the unit of momentum, a kilogram times a meter per second. And with a dot between the kilogram and the meters per second. And this is constant. It's not going to change. The final momentum is going to be the same. So on the final momentum, since they're stuck together, we can treat them as one mass. So 5 kilograms plus 10 kilograms times the velocity. 5 plus 10 is 15 kilograms. And we can divide both sides by 15 kilograms, which cancels out on that side. And we get a final velocity of 3.333 carried meters per second. The test, even though one very good indication that this was inelastic is because they stuck together. Let's calculate the energy beforehand and the energy after. So the total kinetic energy beforehand. What's the equation for kinetic energy? Yes. Something you definitely need to memorize as energy. Conservation of energy is very useful. Sometimes you'll be given a problem and It's very complicated to solve, but if you remember conservation of energy, it becomes easy to solve. So beforehand, we have 1/2 times 5 kilograms times 10 meters per second squared. That's equal to 250 joules of energy. And afterwards, we have 1/2 times 15 kilograms times 3.333, so on, meters per second squared. And we're left with only 83.333 carried joules. So that means, by the way, math symbols. This symbol right here, I'll start using this more often. All right. So this symbol right here means therefore. It's the mathematical symbol for therefore whenever you're writing notes. So therefore, (166.66 carried joules of kinetic energy was lost, meaning converted or transferred into sound, heat, or deformation. Due to the boxes colliding. This is another reason why momentum is taught after energy. Because so I taught you energy, and if you tried to use the fact that energy is always conserved, you have to always realize, especially when it comes to collision, that energy is going to most often be lost due to sound being produced, heating up. Actually, there's a nice video. Let me see if I can find it. Action Lab YouTube channel took a bag of sand, raised it up, and dropped it. And the bag of sand bounce. So that means it is very inelastic. You could think of elastic collisions as something that perfectly bounces. Like if a basketball was 100% elastic, it would just sit there and always return to the same height. It'll always bounce up and it'll never stop bouncing. Inelastic is where some of it's going to be due to heat loss. But that means that almost all of the kinetic energy was transferred and transformed into thermal energy. And he sits there and picks it up, drops it several times, and you can actually watch the temperature of it actually increase. And I won't be able to find the video of it. Oh well. So let's do an elastic collision. Whenever you are told that an elastic collision has occurred, you should always remember kinetic energy is also conserved. So suppose we had now a 5 kilogram billiard ball moving at 10 meters per second, and it strikes a 10 kilogram billiard ball with no velocity. And let's say that the ball hits let me make sure this works out. So at the end of this, we're going to have two balls. Let's see. I'm trying to debate whether or not I need to give you anything. I'm going to say it's going to be moving at some velocity v1 and some velocity v2 here. I think I don't have to make up any numbers for this. I think this is good enough. If not, I'll add numbers later. So let's apply our law of conservation of momentum. Here, we're going to have that the sum of momentums before the collision has to equal the sum of momentums after the collision. So that means that before, our momentum is mass times velocity. And it has to equal the momentum after the collision. So we can do a few simplifications here. This is just going to be 50 kilograms meters per second. Now equal 5 kilograms times V1 plus 10 kilograms V2. And we can also, so we have one equation with two unknowns. If you have two unknowns, how many equations do you need to solve for the two unknowns? What's the minimum? Two. Ella? Sure will. Because this is an elastic collision, we know that kinetic energy is also going to be conserved. So, law of conservation of momentum, or no, law of conservation of energy. One half times 5 kilograms times 10 meters per second squared plus 1 half times 10 kilograms times 0 meters per second squared has to equal 1 half times 5 kilograms times v1 squared plus 1 half times 10 kilograms times velocity squared. This is 0, so that cancels out. 1 half times 5 times 10 squared is 250 joules, equal to 2.5 kilograms times v1 squared plus 5 kilograms times v2 squared. So we have two equations and two unknowns. That means that we can solve for the two unknowns and figure out the velocities. Do you know how to solve? Do you know how to solve this? Algebraically, given two equations, how to solve for the variables? Alright, gonna remove units to make these easier. I'm just writing. So we have 50 equals 5 v1 plus 10 v2. And we have 250 is equal to 2.5 times v1 squared plus 5 v2 squared. So these are our two equations. Simplest thing is to solve for one variable and then plug it into the other equation. So let's do that. Let's solve for v2. Or let's solve for v1. So 50 minus 10 v2 is equal to 5 v1. Moving this to the left side. Divide both sides by 5. That would be 10 minus 2v2 is equal to v1. Right? Follow? I moved this to the left-hand side, and then divided both sides by 5. So this is what v1 equals. So I can plug that into this equation. 250 is equal to 2.5 times 10 minus 2v2 squared plus 5v2 squared. Do you know how to do 10 minus 2v2 squared? So, let me just get a new piece of paper. Alright. So, 10 minus 2v2 squared. That's the same thing as anything squared is just itself multiplied by itself. You can solve this in two different ways. You can use the FOIL method. 10 times 10 is 100. 10 times negative 2v2 is negative 20v2. And now this one, this times that, is negative 2 v2 times 10. So 10 times that is negative 20 v2. And then this. Negative 2v2 times negative 2v2 is a positive 4v2 squared. Right? And then you can group it together. 100 minus negative 40 v2 plus v2 4 v2 squared. This is known as the FOIL method. Another way of doing it is the grid method. So we have a 10 minus 2v2, a 10 minus 2v2, and 10 times 10 is 100. 10 times negative 2v2 is negative 20 v2. Negative 2v2 times 10 is negative 20 v2. Negative 2v2 times negative 2v2 is positive 4v2. Add up everything, and we can get the same result here. Either way works. Also, you can just remember that a plus b squared is equal to a squared plus 2ab plus b squared. Because if you did the same thing, it's going to be this one. That's just a generic expression. This is used so much that I haven't memorized. But we end up with, thus, 250 is equal to 2.5 times 100 minus 40 v2 plus 4 v2 squared plus 5 v2 squared. Distribute the 2.5 into the equation. So 2.5 times 100 is 250. 2.5 times negative 40 is negative 100. 2.5 times 4 is 10. So now we group like terms. So we have a v2 squared and a v2 squared. This is 15 v2 squared. I'm going to also subtract 250 from both sides, which cancels that out, giving us 0 here, equal 0 minus 100. And so we end up with an equation. 0 equals negative 100 v2 plus 15 v2 squared. Following so far? All right. So all we have to do is now solve for v2 squared, or v2, I mean. So one thing you could do is the quadratic equation. This is a quadratic formula. Another thing you could do is move this to the other side. So we got 100 v2 is equal to 15 v2 squared. I can divide by v2. Note, when you divide by a variable, you lose a potential solution. Because when you use the quadratic equation, you always get two answers, right? What number can V2 not be? Because you cannot divide by 0. V2 may be 0. And thus, if you solve by division, you lose this potential solution. If you were to solve by the quadratic equation, it's going to come up with two answers. It's going to come out with 0 as one of the possible answers, because 0 can work. Why can 0 work? What happens if this ball just phased straight through it? Well, energy would be conserved, right? Because it never hit anything, its kinetic energy would be unphased. It will still be moving with 250 joules of energy. The momentum doesn't change. And again, physics states that these will always work. Again, remember when we were launching things when we were launching it off the cliff, we had another solution where it goes back in time. Same thing happens here. It is possible for it to just go straight through it. This would be as if this is elastic, so there can't be any deformation, but there are some particles that can just go through things. So, for example, an electron can quantum tunnel through something, in which case this would be an example. Just note that whenever you divide by this variable, you're removing a potential solution. So this V2 will cancel out with a V squared here. And so we're left with 100 is equal to 15 times V2. We can divide by 15. And we get that V2 is equal to 6.66 carried meters per second. So that solves for one velocity. We can solve for the other velocity by plugging this into this original equation. We know that V1 is equal to 10 minus 2V2. So we can plug this back into the original equation. We could also plug it doesn't matter which equation we plug it into to solve. So 10 minus 2 times 6.66 6 carried. And that's equal to negative 3.333 carried meters per second. So that's our final solution. So if a 5 kilogram ball moving at 10 meters per second struck a stationary ball, then after the collision, what would happen is this ball would be moving, it's negative, so it'll be moving in the opposite direction at 3.33 carried meters per second. And this ball would be moving to the right at 6.666 meters per second. So if you had two balls where one was twice the other, and you would see something similar. You see, think about it, this one's so massive, it's going to want to bounce off of it. Let's say that this had infinite mass. It would be like throwing the ball at a wall. You can treat the wall as having infinite mass or unmovable. What happens when you throw a ball at the wall? It bounces off. So we'd expect that it would bounce. Some of the momentum is going to transfer into the other object, and we're going to see that it's going to bounce off like that. Or this one's going to move to the right, so not all the momentum is transferred backward. Does that make sense? So elastic collisions is slightly more complicated, as you can see, as you're going to have to basically do this. Law of conservation of energy and momentum together, and then you're going to have to do a whole bunch of algebra to solve for it. The trick for the algebra is we have two equations, solve for one variable in one equation, and plug it into the second. And then you just do pure algebra to solve for the missing variable. Note, however, when you divide by a variable, you do lose the potential solution. If you were to use the quadratic formula to solve this, with some of them you have to use the quadratic formula. It's just in this case it was even nice worked out. The only reason why I was able to do this division is because the 250 and the 250 here canceled each other out. If this ball here wasn't stationary, this would not cancel each other out, and you would have to use the quadratic formula. And you will get two possible values. I just want to say one thing real quick. You have to then realize, are both solutions feasible? For example, if you have one ball going through the other, that usually indicates that's not going to work. You can't have this ball moving faster in the right direction than the other one without going through. That's the only thing you need to know. What's up, dude? Have a good break? No, it's not. Well, every time so everywhere we had it on a deal to shoot in the air, but it fell over. What? That was at the very beginning of the year. Wow. And then y'all very, very slowly, manually moved it to the wall. Yep. It was that far away because I had enough room to up in the cart and everything very well. No, it was enough for the door to completely open on the cart. No. Be quick. Oh, if you, If y'all are curious about physics, this is one problem. This is the